Okay, so this is Chapter 9, Section 5, which is chemical reactions are driven by the spreading of energy. Energy tends to disperse. It flows from where it's concentrated to where it is spread out. Energy does not concentrate unless you put some energy into it to make that happen. An example is that when you turn on a stove, the heat spreads out into the cooler room. The concentrated chemical energy that's in gasoline disperses in the formation of many very hot small molecules that scatter explosively within the piston chamber, which you can see happening in this graphic. And then they go out the exhaust pipe and into the atmosphere. The flow of energy is always a one-way trip from where it's concentrated to where it's less concentrated or spread out. So the second law of thermodynamics is any process that happens by says that any process that happens by itself results in the net dispersal of energy. Heat will naturally flow from a higher temperature object to a lower temperature object because in doing so energy is dispersed from where it's concentrated to where it is spread out. Now we can make heat flow the other direction. That's how air conditioners work. That's how heaters work, and that's how our refrigerators and freezers work. But we have to put energy into it for those things to happen. That won't happen naturally. And the second law of thermodynamics is about the direction that heat naturally flows, not how we can make it flow in the other direction by putting more energy into it. So entropy is a measure of this natural spreading of energy. Whenever there is a spreading of energy, there is a corresponding increase in entropy. Entropy is usually defined as the measure of disorderliness. So things become more disorderly, more messed up as time goes on. That is the natural state of things for things to fall into disorder. So the sun is a prime example of the fact that energy has a natural tendency to disperse. So the whole point of this is to figure out when we put two materials together, are they going to react to form new materials without you doing anything? Or are you going to have to put some energy into it to make the reaction actually happen? So when we put these two things together, whatever they are they still going to just sit there? Or are they going to react together and form something new? Now, it's maybe that it's possible for them to form something new when they react together. The question is, are they going to react together naturally without you having to put any energy into it first? So, if there is an energy dispersal that happens as a result of these things coming together, then it is much more likely that they will go ahead and react without you putting any energy into it. So if a reaction results in the spreading of energy, which means there's an increase in entropy, then the answer is yes. When you put these two materials together, they will react to form new materials. So if the reaction results in the concentration of energy, which is a decrease in entropy, then the reaction will only occur at the expense of some greater energy dispersing process elsewhere. So sometimes if there's one small thing that will result in the concentration of energy, but the next reaction will be an even greater dispersal of energy, then the reaction will go ahead and happen. And the formula that you see down here at the bottom of the screen is sunlight plus 6 carbon dioxides plus 6 water molecules forms a carbohydrate plus oxygen, 6 oxygens. That carbohydrate is the plant sugars that plants form in the process of releasing oxygen. So there is a close relationship between entropy and our psychological sense of time. We expect energy to disperse. As we witness this dispersal of energy, we get the sense that time is moving forward. If you see a broken coffee cup float up into the air and form itself back together and end up on a table, you're going to have an idea that time is running backwards. It's probably a film being shown backwards because that's not the way that it happens. So in real life, if you saw smoke going into a smokestack rather than coming out of it, or if you saw flames and heat being absorbed by ashes as they change from ashes into wood, then you would think that time is running backwards. So we do have this kind of natural sense of entropy that we expect things to become more disorderly. We don't expect things to become more orderly on their own without an input of energy to cause that to happen. So the idea behind all this is you can't win because you can't get any more energy out than what you put in. You can't break even because some of your input energy is lost as ambient heat. And you can't get out of the game because you need thermodynamics in order to survive. So entropy happens. And that's it for this section.